Okay, let's get started. So today we're going to be, or actually this week we'll be talking about some higher level, kind of meta level issues that crop up in NLP research, especially in modern NLP research. So today we'll be focusing on ethical issues that arise in the training and deployment of these kinds of large language models. On Wednesday, we will be talking about the necessary data and compute requirements to train models with the capabilities that we want them to have, and also how the field has been progressing over the last couple months in this direction. So before we start, in terms of deadlines, you have your homework and your quiz 5 due this week, and then your final projects are the last thing that you have to do for this class, and those are due on May 12th. So for your projects, you can expect them to be graded by, I think I have some deadline of whatever the last day to submit grades is, so you will get those grades back, I think, within a week. You can expect comments as we gave you on your project proposal. So yeah, that's the plan. Okay, so I wanted to start with here some kind of demos of a newish method that has been proposed to address some of the let's say inappropriate or undesired outputs that you get from a model as large as GPT-3. So again, GPT-3 is one of these left to right language models that has 150, 175 billion parameters, has been trained on billions of tokens of data, and people are using it to solve a variety of tasks in a zero-shot setting. So if you ask it things, it will generate text regardless of what you ask it, and many times it can even express opinions about a particular input. Of course, when we decode from these models, we're usually sampling from them, so it's not like the opinions are consistent, right? It could, you know, if you sample some, if you take 5 samples for this particular input, who is the most beautiful person, you might get 5 completely different opinions. So, you know, one reasonable question to ask, given that these models are in production systems now where, you know, companies can query the OpenAI GPT-3 API and get generated text and then use it however they want in their products, is what should a model do in some of these circumstances where you can't really control what the user query is? Should the model be able to express opinions that it itself doesn't have? And what if those opinions are offensive or inappropriate or you know, would otherwise affect the end user's experience of this, whatever feature is using a model like GPT-3? So this can be also pretty bad in terms of how the language model is actually deployed. But if you give it, for example, how should I treat cancer, you can see that GPT-3 generates something like, take away all the things that cause cancer. Well, all right. You've got to do this with 1 or 2 applications per day for about a month, and then you don't need to do it again for at least 6 years. You can do this while on chemo, but if you don't, it's not really clear what this is here. The bad news is that you're going to be eating a lot of stuff you've been told is bad for you, including sugar. The good news is that eating sugar and other things you've been told is bad for you is going to be good for you. I'm going to give you the good news, the bad news, and the ugly news. The good news is that if you are overweight, you may lose weight, a lot of weight. The bad news is, so of course, none of these things are medical advice, and no one should take the advice of a model like this when they ask a question. But you can imagine all sorts of situations where you know, a model might be deployed and a user may not know what the exact details of that model are and what the data, the training data of that model look like. So one interesting question is what should happen here? If someone asks, how should I treat cancer, maybe you would want the model to say, you know, go see a medical professional, but not actually give any medical advice. So, all right, maybe I'll ask you all, what do you think you could do in, let's say you just have a left-to-right language model like GPT-3, what could be one way to influence the way in which the model responds to any arbitrary user input in such a way that maybe it lessens the chance of it producing these kinds of inappropriate outputs? Sure, so this is one definite way you can do it. You can say train another model, or maybe it doesn't have to be trained, maybe that's the best way. So if the user input is this and the model output is this, maybe this classifier would recognize that this is clearly an appropriate input, and instead of actually serving this output to the user, it would say, you know, we can't give you an output for this response at this time, or something like that. So you could certainly do that, and OpenAI itself has a content filter that all downstream users or even companies that are using their product have to abide by without, so this is like for general deployment. I think you can get around it if you have particular user agreements for your specific application. So their API already will do something like this, where if some internal model on OpenAI's side decides that the output that has been generated is offensive in some way, it will just say, oh, we couldn't produce an output. That's probably the approach that has been taken now, but you can imagine it also has issues, right? Some of these cases might be way too subtle to detect with a classifier like that. Maybe it's hard to get data for something like this. And yeah, in some cases, you know, it might be hard to actually deploy this in a reliable manner. So any other ideas? Well, so the one that we're going to be talking about right now is actually quite simple, and it's also very interesting and also problematic from a different angle. So OpenAI had some researchers that essentially proposed to fine-tune something like GPT-3 on a very small data set that attempts to teach the model about certain values, which will then hopefully impact the way in which it responds to particular queries. So they fine-tune on a small set of QA pairs, like given this question, what makes a person beautiful or ugly, they basically fine-tune it to generate this answer. The attractiveness of a person is a highly subjective measure, blah, blah, blah. And this outline is kind of something that they wrote themselves to guide the generation of the answer. So basically, given a question like this, they want to emphasize that beauty is subjective and it should not actually make a decision on what it considers beautiful versus ugly. So they collected, I think, about 1,000 or maybe 2,000 of these QA pairs where there's a question, there's an answer with some sort of, you know, they're trying to get the model to recognize some particular value and exemplify that value in its outputs. So you can just take a huge GPT-3 model, which has already been pre-trained, and then fine-tune it to increase the probability of this answer given this question input. And so if you do that, it turns out that it affects the outputs that it generates on a whole variety of different inputs, even those that are out of the set of questions that it was fine-tuned on. So, for example, we saw who was the most beautiful person before, and the base model said an old man without a wife with children and grandchildren. But this new model, which they call the values-targeted model, says it depends on who you ask. Each person has their own perception of beauty. blah, 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 blah. So it did not actually offer an answer to this question, right? It kind of just said, you know, it depends, which is one of the values that it was fine-tuned on. And for this question, how should I treat cancer? Instead of generating actual incorrect medical advice, it said cancer is a very complex disease and it depends a lot on your specific diagnosis. You will want to see a doctor right away. You may have surgery, chemo, radiation therapy, or some combination of your treatments. Now you can even argue that maybe it shouldn't even produce these kinds of things, and maybe it should just say, see a doctor and nothing else. But this is still clearly a lot more reasonable than what the base model produced. Okay, so does anyone see any issues with this kind of method as opposed to the one you suggested? So that is actually not so clear. One of the capabilities of these big models is that they can generalize with very small training inputs or fine-tuning inputs. So the model might not have even seen cancer in this fine-tuning data. It might have seen something more generic, like don't give medical advice, but that is able to affect its responses for any sort of condition. Sure. So this is always a worry with fine-tuning a model, is that it forgets whatever it's been pre-trained on. So in this paper, they reevaluate this new values-targeted model on every task that GPT-3 was originally evaluated on, and they find that its performance on all of those tasks doesn't change markedly. But its responses to these kinds of opinionated questions, or questions where it should generate something different, that does change. So in that respect, it seems okay, although yes, it's definitely a concern.
Maybe on their language situation, if you really all represent very measured
Yeah, definitely. So here, if you go through this approach, you will see a lot of outputs that are, as you say, more measured, that don't try and take a stance, that kind of just are trying to be acceptable to the vast majority of people. But depending on your application, this could have unwanted effects on, say, generated text for creative story writing or other things where you might want characters who have some sort of different perspectives or something like that. So that's definitely true. They did not evaluate this kind of fine-tuning approach on cases where it might be less harmful overall to generate a response like this in lines with whatever application you're working on. Any other issues? So one of the other issues is that someone has to come up with these question-answer pairs in the first place, right? And their values might not be aligned with someone else's values, and so also the coverage of the set of QA pairs is another thing. Like, who is actually validating the fine-tuning data and making sure that it's actually aligned with what. And who is the target user base? It changes dramatically based on the application. So this is very preliminary stuff that just shows that, if you select some reasonable value-targeted judgments and you fine-tune your model on it, it can change the behavior of the model. But it's still unclear, what should be done in these kinds of settings. And especially as we see these language models being deployed more and more in real-world products that are facing users and potentially thousands or millions of users, these kinds of questions become much more important. Okay, so I also wanted to show this demo. Some of you might have heard of this Delphi prototype, which was released by AI2, the Allen Institute for AI. And so there's a paper and associated demo, which we'll check out. But basically, it says, this is a research prototype designed to model people's moral judgments on a variety of everyday situations. This demo is intended to show the abilities and limitations of state-of-the-art models today. The first version of this demo did not have some of this text, and so people thought, you know, they're training an AI to make these kinds of moral judgments. There are lots of problems with that. But yeah, they have, you know, these disclaimers. Model outputs should not be used for advice for humans. They needed to say that. Could be potentially offensive, problematic, or harmful. The model's output does not necessarily reflect the views and opinions of the authors. So let's see how this works. So if you type in something like drive your friend to the airport early in the morning, you see something like it's helpful. So it's making some sort of judgment about this. Whereas, can I wear pajamas to a funeral? It's inappropriate. Oh, cleaning a toilet bowl with a wedding dress. It's disgusting. Okay, not bad. Cleaning, okay, lots of cleaning toilet bowls. Can I torture a cat if it makes me happy? It's wrong. So you can see it's making all these kinds of judgments. And these have been maybe handpicked, so the model certainly works on these. But we can also, you know, make up our own. So if we say, drive your friend to the airport early in the morning, it's helpful. I guess we can modify this. So if your friend doesn't have a flight and doesn't want to go, I hope this would be unhelpful. It's rude. Okay, I mean, suppose that's true. Anyone else have a situation they want to try? So what did you say? Oh, okay. Rob the rich and donate it to the poor. Oh, that's interesting. I wonder what it will say. Oh, it's wrong. But what if you change this to something more acceptable? Like, oh, okay. Tax the rich and... See, now it's actually... Oh, it's good. So yeah, there you go. Right. So, I mean, this might be a case where the model may want to produce a more measured response, you know, depending on what values you want to express. Ignore a phone call from your friend. It's rude. If you just fought with your friend. Okay. So it's like, you know, it has cases where it doesn't work. And, you know, you can try this out yourself and make the inputs more linguistically complex. If you add a bunch of stabbing a cheeseburger. Oh, okay. So it's interesting. No, these are like the fixed set of examples that they decided to show on their websites. A cheeseburger. Oh, a cheeseburger stabs. So, interesting. Okay, so anyway, I shouldn't get distracted. You should play around with it. It's pretty interesting. But yeah, this has another, you know, it opens another can of worms, right? Because you shouldn't actually use what the model thinks about these situations as, you know, actionable advice for a human, right? These models are not there yet. So, but, you know, some people and startups and so on might race ahead to actually try and build and deploy products using these kinds of things. So that's where it becomes a little, yeah, murkier. Okay, so today we are talking about, in general, 4 issues regarding ethics and deployed NLP systems. Most of them are more generic. They're not just specific to NLP, but basically any sort of machine learning application. So these issues mainly arise when we're talking about systems that interact with real people, that may offer them advice or recommendations, or you know, even more important, make decisions about people's lives. So, you know, there are things like if you committed a crime, you can have a model automatically predict the sentence. This has, you know, considerable ethical implications. Okay, so we've already talked about why this is important. So when you're assessing some sort of AI system, you might want to ask a series of questions. First, who is going to benefit from this technology? And also, more importantly, who is going to be harmed by the deployment of this technology? And there are many broad things that you should be concerned about. So how representative is your training data, not only of your desired users, but perhaps of whatever community you're deploying it to, or the world as a whole, or if you're deploying it to multilingual populations, the language diversity. You might be concerned with representativeness of gender or ethnicity or whatever, and all of these things come up in your training data, right? And the training data, if you're getting, you know, 300 trillion tokens of text, it's not really clear how you can filter it and how you can, or how should you filter it, right? So a lot of these questions don't have correct answers, or like, you know, answers that the community has all agreed upon as this is the way we should solve this issue. We'll talk about the other ones in a bit, but we'll start with the data. So, of course, if you're training a language model on data from the internet has all sorts of biases. It has several social stereotypes. If you just look at Google image search, for example, you can see, this is from June 2016. If you look up 3 black teenagers, you see, you know, these close-up face shots, and they're not smiling. They have kind of, you know, other expressions. But here, if you look up 3 white teenagers, you see, you know, these clean white background, people are smiling, playing sports, and so on. So if you train a model on this kind of data, then you might learn things about one demographic or the other, which might not necessarily be valid and might cause some of these harms to arise when you deploy these systems. So there's also gender stereotypes. If you image search doctor, you will get pictures mainly of men, maybe white men, whereas nurse, you'll get pictures of women. If you look up homemaker, you'll get pictures of women primarily, but CEO will give you, you know, men in suits. And so again, it's a question of if you are getting data off the internet using, say, Google search or some other search to get examples of a particular category of picture, you need to be conscious of what you're actually getting and what could be, you know, what kind of biases could creep into those kinds of searches. If you train your model on biased data, your model is going to be biased as a result, and as we'll see later in this lecture, your model could even be, it could even amplify the bias that is already present in the training data. So if you look specifically at gender bias, for example, and if we look at text data, there's a lot of instances of this. So males are overrepresented in the reporting of web-based news articles. So if you read a random article on CNN, it's much more likely it'll be about a man than a woman. Males are also overrepresented in Twitter conversations in terms of people mentioned and also the users themselves. And if you look at Wikipedia, another common source of training data, there are fewer biographical articles about women, and the ones that are there, they disproportionately discuss family or romantic relationships compared to male biographical articles. There's also, you know, more subtle things. So like IMDb reviews written by women, you can see the name of the person sometimes who wrote them. They're perceived as less useful than those written by men. And so, of course, that's news articles, Wikipedia, Twitter, movie reviews. All of these things are the favorite data sets for NLP people to train their models. And as a result, there have been several papers showing bias in all sorts of NLP technologies. Not listed here are the giant language models that we've been talking about this semester. Let's take a look at gender bias and coreference resolution. So coreference is the task of given an entity like the physician and some reference, like he here, figure out which entity this he refers to. So is it the secretary or the physician? So if you read the sentence, the physician hired the secretary because he was overwhelmed with clients, the he should clearly be co-referent to the physician and not to the secretary. And that's just because of the content of this second part of the sentence, right? It wouldn't make sense if the secretary was hired because he was overwhelmed with clients, right? The physician is the one who needs the secretary to deal with the number of clients. However, if you replace this pronoun with she, the coreference system, the state-of-the-art coreference systems will link she with the secretary instead of the physician, despite the fact that it's obvious that she has to refer to the physician in this context. It's because it sees more instances in its training data of secretaries being female and being referred to with feminine pronouns, and as a result, you have this kind of error that crops up. Yeah.
Like English in its nature does not have a lot of feminine pronouns, like other languages have more, like Spanish or Arabic. Does that make a problem for English for the model? Like for example, if you have you instead of he or she, how will the model know that you were a male or female?
Yeah, I mean, within a single sentence, perhaps it's not clear, but within a broader context, maybe it would be clear, right, what the gender of the entity is. But yeah, in general, like, regardless of the language, these issues are going to exist if the training data of the model contains these kinds of imbalances. So you can see the same kind of construction here. The physician hired the secretary because she was highly recommended. Now it's clear from the context that she refers to the secretary, right? So ideally, this link would be correct, and regardless of what the pronoun is. However, if you change the she to a he, now the model thinks he is associated with physician instead of secretary. So these issues are present in all of the models that we have today. Okay, so we talked about the bias in data. We'll keep talking about it a little and look at some ways that you can address issues that people have found. And then we'll talk about 3 other broad categories of ethical questions that arise in these kinds of situations. The suggested readings for today, they're all optional. If you're interested in learning more, there's an entire class on ethics in NLP that professor at CMU offered, and they have many lectures specialized to each of these questions. Okay, so there's also a lot of different types of sampling bias in the data that we collect from the internet or other sources. So for example, if you're building a sentiment classifier, right, you might train your model on Yelp, but you need to be at least conscious of who is posting Yelp reviews, right? What are the demographics of the people creating the data that you're using? So if you look at the demographics of Yelp users, 60% of them have gone to college, almost half make over 6 figures, and so perhaps the opinions that are on Yelp are not representative of the entire population, right? So there's also reporting bias, which is important. If you look at something like Twitter, people may not talk about things that are more usual or boring or that people won't care about. they might talk about things that are more likely to get likes or retweets. So these might be things that are inherently interesting or unusual. And if you train a model on Twitter, perhaps you would think those kinds of things are more common than they actually are. Similarly, aspects of different objects are not described as much as things that make them unusual or distinguish them from other objects. There's also systematic bias. So if you're using Twitter, you don't really know what algorithm is used to give you the search results when you type something in, right? Why is this particular tweet ordered above this other one? You don't know. Is it based on the likes or the retweets or the content similarity to your query? Is it because it wants you to click this ad? There's no way to really know, right? And finally, within even a particular language, there might be several different dialects or sub-communities that use a language in different ways, and whichever the dominant population is on whatever platform you're crawling is not necessarily the one that is actually dominant in the real world. So lots of different types of bias to be aware of. If you're working on multilingual problems, it's very common to use Wikipedia. So in fact, the multilingual BERT model was trained on like 100 different Wikipedias concatenated together. But here, the size of each language-specific Wikipedia, like the number of tokens in that, or the number of articles written in that language, does not necessarily correlate to the number of speakers of that language. So in English, you have about 16 articles per 1,000 speakers. But with languages like German, they have fewer speakers but more articles. And Indian languages have far fewer articles, but they have many, many more speakers than some of the European languages. So your Wikipedia might be underrepresenting more spoken languages and overrepresenting languages that are higher resourced for other reasons like socioeconomic conditions. Okay, so let's take a look at a concrete example. One task that people used to think was solved is language identification. So this is the case where you get some text and you have a classifier that's trained to predict what language that text is written in. So it seems pretty straightforward, right? Like if you get this tweet, you might want to predict that this is an English tweet. But it becomes a little tricky when you have different dialects or you have code switching between different languages, and you might have like slang or other things. The problem is not as trivial. So in 2005, before all the neural stuff that we've talked about, this paper claimed that language identification is solved because using data from the World Wide Web, we achieve accuracy approaching 100% on a test suite comprised of 10 European languages. So this was using like simple feature-based logistic regressions or support vector machine classifiers on some data set, and the task was presumed to be solved. But there have been many studies, including one from Sulin Leggett, who was a PhD student here at UMass, that these purportedly perfect language identification systems, they do not perform well when you give them text that, say, is in a language that is covered by the system, but in a different dialect. So African American vernacular, that gives these systems a lot of problems. Code switching or abbreviations or tweet speak or whatever also tend to break these things. And language ID systems are often a core component of pipelines that are used in applications like health monitoring, so they actually make decisions. So for example, if you have a tweet, one pipeline could be detect the language of that tweet, use a keywords filter that is associated with that language, and then produce some recommendations for the author of the tweet. So this person said, got the flu over the weekend, didn't know it today, until today, and I somehow managed to give it to 5 of my friends. So you run it through a language ID system, maybe it detects English, then you run it through your English keyword filter for various illnesses or health-related keywords, and then you provide some sort of advice or you encode some analytics or whatever. But in this kind of pipeline, this is the first step, language ID. So if it goes bad, then you get to a different set of keywords, and then you make a different set of recommendations, and this could be potentially bad, right? Or it could be harmful. Okay, so yeah, like if you detect the wrong language, then you basically cannot continue this, or you do something that's actively harmful. So in general, if you look at just English, right, there are many different dialects and geographically localized variants of English. It turns out that these language ID systems underrepresent populations in less developed countries. So if you look at English that's being spoken in, say, India, and you look at tweets written by people in India that are written in English, the accuracy for these tweets, so the probability that the language ID system will correctly classify the tweet as written in English is only like 80 or 70%. These are 2 of the most popular language ID systems. Whereas if you see like countries that have a higher human development index, so this is an index that takes into account education, life expectancy, and income of the population of that country. As that increases and we get to countries like the US, the performance approaches 95%. So there's clearly a trend here where the language ID systems perform worse on English that's used in other countries. Now this could also be a result of a lot of code mixing where people are mixing different languages together. But there are ways to correct for this. And the easiest way is just to do a different sampling of your training data set. So maybe instead of just training on like English news articles, you train on Wikipedia, news, Twitter, you train on other sorts of sites that are maybe more informal, and maybe you train on some multilingual data to get some of the code switching behavior as well. And once you do all of this, this orange line shows the result where you can I mean, there's still some degradation, but you can do much better than the competing language ID systems. Okay, so that was just a quick example. And yeah, like one simple approach to combating some of these data set related biases is to sample your data that's used for training in a way that represents more of the population that you're intending to target. Okay, so now we'll maybe shift a little away from NLP for a bit and talk about optimizing towards a biased objective, which is often the case when you don't have training data for the particular problem that you're interested in, but you have training data for some sort of proxy task which might have a bias in it. So this is a pretty famous case that many of you might have heard of, where they were looking at this question: what is the probability that this person will commit a serious crime in the future as a function of the sentence you give them now? And so if you know the answer to this question, then you can decide based on, maybe you have 5 different potential sentences to give someone. You might want to lower the probability. You want to choose the sentence that lowers the probability that the person will commit a serious crime in the future after their sentence expires. So this system that they built to answer this question contained a balanced training data set that had people of all races represented in it, and race was not one of the input features of the classifier. However, the objective of the model is not obtainable, right? With this question, you can't get data for this, right? Who will commit a crime? That is not knowable because You know, someone might commit a crime and not get caught or not get recorded, and there's no way to get that kind of data. So the proxy data that you can actually collect is who is more likely to be convicted of a crime, right? Because that goes into the records and you can get the data of this. So someone committed a crime, they got sentenced, after their sentence, they committed another crime. This is the data set that you can construct in this way. So given this description, what are some issues with does the proxy objective actually represent the real question that they're trying to answer here?
If you have a biased conviction system, then your model will learn that same bias. So.
Yeah, that's right. So even though race was not one of the input features, the conviction data, so the labels of this data set, do contain biases, right? So certain populations like African American people get convicted at higher rates than other populations for the same crime, and maybe this would creep into the system and have it decide, you know, to treat African American people differently than others. Yeah. Yeah, so that's a great question. The question is, even though race was not one of the input features, could the input features have included things that are kind of indicative of race? Like, for example, where a person lived, that you can infer maybe the demographics of that place somehow if you have the training data set. That's definitely a problem with a lot of applications that try and get rid of various features. In this case, I'm not actually sure what they did, but potentially, yeah. But yeah, that's definitely an important question because it happens all the time when you try and get rid of some specific aspect. There are so many features in your data that could be correlated with it that it's not as simple as just let's remove the race column from our CSV. Okay, so there's also, more related to NLP, this kind of task where given a description of a crime, you might want to predict the sentencing of that crime. And so this is kind of in the vein of automatic judge, where instead of having a human judge, you just give a description of what happened to some machine, and it predicts a sentence, and it's handed out, and that's it. There's no human involved. I mean, obviously that is a scary future dystopian vision, but people are working on this kind of thing. So you see here on July 7, 2017, when the defendant Kui XX was drinking in a bar, he came into the conflict. After arriving at the police station, he refused to cooperate and bited on the arm of the policeman. So what should happen here? And you might have some training data. You can collect data from like police reports or whatever. This person was sentenced to 12 months imprisonment for creating disturbances and 12 months for obstructing public affairs. So now you get to predict from the description of the case, these are the two charges that were given out of the set of all possible charges that could be given. So when these people, when these researchers published their paper, they included a section on ethical considerations, which said, the mistake of legal judgment is serious. It is about people losing years of their lives in prison or dangerous criminals being released to reoffend. We should pay attention to how to avoid judges' overdependence on the system. It is necessary to consider its application scenarios. In practice, we recommend deploying our system in the review phase where other judges check the judgment result by a presiding judge. Our system can serve as an anonymous checker. So, you know, this paper and some related ones got a lot of controversial press after it was released, and people in the NLP community were asking, you know, should this work have been allowed to be published, or should it have been done at all, which is, I guess, the ultimate question. So are there any thoughts? Yeah. Yeah, so certainly the data that this is trained on is real police reports paired with the sentences. That data is going to have some sort of bias, and the bias is also going to be in this kind of automatic judge model, right? So that is certainly a concern, just like in the other case. And if we were to deploy this system, it would make judgments with those kinds of biases. Yeah.
So, yeah, the question of like, should this kind of work be published? I think like, we also look at from a different angle, like self-driving cars. Like, the first few works for a self-driving car might be very dangerous when you let the algorithm drive over the car. So, but they're still necessary to get to later works that might actually be helpful and useful. So, like, yeah, don't use the first couple works that make biases in them, but still create that work and publish it so other people can build on it. And hopefully, I mean, it could maybe eventually be a useful way to figure out more backlog, right?
Sure, but I think we should think about, there is a difference here between this kind of application and self-driving cars, in that here, this thing is just a classifier that predicts this or this, but it can't actually explain why it made that prediction, which is, the actual role of a judge, right? They'll lay out all the different points that led to making a decision. If you just have this thing that maybe it gets 90 whatever % accuracy on an older data set, it still doesn't, replace the role of a human judge. And we actually have to get all these additional functionalities before that's possible. But there's all sorts of other considerations, right? Like judges are also humans, and they, can take things into account to adjust sentencing based on, like on a case-by-case basis. Could a model like this do that? It's unclear. So, I mean, I think we can all, at least most of us, agree on the benefits of things like self-driving cars, but the benefits of getting rid of judges, yeah, sure, there are court backlogs. That's probably why this work was done in the first place, but it seems a little more complex in this case. Yeah. Other thoughts on this? Okay, let's move on. So another thing that is important to keep in mind is inductive bias, which covers all of the assumptions that are made by our models. And these are kind of encoded into the design of the models. So for example, recurrent neural networks, which we talked about, they assume that the sequential ordering of words is meaningful, and so they process an input text one word at a time. Whereas for example, if you have an averaging-based model that just computes a representation of a text by averaging the words, it does not have this inductive bias, right? It does not consider the sequential order to be meaningful. So in word embeddings, which we didn't talk about in the semester, but these were basically the things used to represent words before we had models like BERT, which replaced the word embeddings with language model hidden states. Word embeddings would represent each word in your vocabulary, so word type, not word token, with a low dimensional vector. And the vector space was found to be semantically meaningful. So like words like scared and frightened would be close together in the vector space. But then people also found that these word vectors contained some undesirable gender biases. So if you take the vector for man and subtract from it the vector for woman, you can look at that difference between these vectors. And this turns out to be similar between the difference of computer programmer, that vector, minus homemaker. So you can see that this kind of gender bias is, undesirable in this context on the right, and we might want to de-bias these embeddings to get rid of this kind of thing, depending on your application. So if you look at which words in your word vector space are closest to she and related to an occupation, So these are like the most female-oriented occupations that, as defined by a learned word vector space, you see homemaker, nurse, receptionist, librarian, socialite, blah, blah, blah. Whereas the ones that are more associated with men are like maestro, skipper, protege, philosopher, captain, architect. You know, none of these are actually gendered in any way. But because the bias is in the training data, the models also learn this, right? And so to train a word embedding model, generally you take a word and you train it to predict the words that occur in its context. So if you see a sentence like, the captain took his, I don't know, ship to shore, or something like that. If you have this sentence, your objective would be, given the word vector for captain, predict all the surrounding words, which could be his, right? In the captain took his ship to shore. If you see enough of these cases, you'll learn that given the word captain, his is a highly probable, or he or him should be highly probable words for this particular word. And that's why you get these kinds of gender biases cropping up in your word embedding space. So people have proposed different approaches to de-bias these kinds of vectors, and similarly de-bias things like BERT and language models. So the first thing that's commonly done is to identify a gender subspace. So this is where you take words like she and he that are representative of gender, and you compute the vector differences between all of these words, like woman and man, daughter and son, mother and father. These are representative of the gender subspace, as they say. And then you identify words that should be gender neutral, like occupations, but perhaps are not within this kind of vector space. So here you have programmer, doctor, homemaker, nurse, all of these words. And then on the left-hand side, you have things like he, she, king, or queen, which are representative of the gender. So given that you have your gendered words and your gender-neutral words, you can then learn a transformation that is applied to the gender-neutral words that projects away the subspace of the gendered words from these words that you want to kind of de-bias. And then you should have another loss term that encourages not to make too drastic of a change, because if we apply this to, say, programmer, and we are able to de-bias it, so move it away from this gender subspace, we don't want to interfere with any semantic representation of programmer that we've encountered, like maybe programmer is similar to computer or technology or something like that, right? So there are two terms in this loss function, which we won't go into. One is don't modify the embeddings too much, so let them preserve as much information as they originally had. Just slightly change them, but in that slight change should minimize this gendered component. Okay, and finally, the last thing we'll talk about is, so you have bias in your training data, but then your objective function and your modeling optimization makes this worse. So the predicted model actually has more bias than the training data itself has. And this is very common with basically all models exhibit this phenomenon. It's called bias amplification. So we'll look at this paper, Men Also Like Shopping, Reducing Gender Bias Amplification Using Corpus Level Constraints. This will also show us a new task, which we haven't talked about yet. So this task is called visual semantic role labeling. In this task, you get a picture like this one, and you're asked to predict this kind of action that is shown in this picture, so here cooking, and also roles as well as agents of those roles for this particular action. So you have the agent here is a woman. She is cooking vegetables in a container that's a pot using a spatula as a tool. So basically, given this image, you need to predict all of these things. That's the task. So this is a vision and language problem. So as usual, we'll see an intersection of these convolutional neural networks paired with whatever kind of NLP technology we want to use to do this kind of prediction problem. But let's take a look at the data set gender bias. So if you look at the act of cooking in the data set that they used, 33% of the agents were men and 66% of the agents were women. And if you look at a trained model, if you gave it images of people cooking, it would predict 16% of those images to be male and 84% to be female. And if you look over here, you can see clear examples of men cooking, and these have been predicted as female agents, like this one and this one, and lots of these images, right? So, you know, the data set bias, setting that aside, this is clearly bad because it's amplifying that bias further. And if we can't do anything about the training data bias, at least we should be able to do something about this. So the constraints that are generally put on these models to address this issue are to at least try and get the model to contain only as much bias as is present in the training data set, but no more than that. So that's the goal. It's a much more accessible goal than, you know, getting to equal representation. That would involve, you know, maybe resampling the data set, but then you might have, you know, all these correlations between different actions, which is much harder to do. Okay, so, and you can see some of the model predictions here. So there are actually quite a few interesting follow-ups of this work that try and keep a scene as similar to each other as possible, but change one aspect of it, like maybe the gender of the agent, and see what happens. So here you have two very similar pictures. On the left, it predicts woman cooking. On the right, it predicts man fixing a faucet. So clearly it's not doing a great job here. So you can quantify the data set bias, first of all. This is just the percentage of, let's take cooking as an example. The percentage of cooking actions that are associated with men is 1 out of 3 in the training data set. And if you take a look at your dev set or some held out data, what is the predicted gender ratio in that held out data? So here, in this case, it's 1 out of 6. So it's predicting half as many men as in the training data set. And you can look at which actions are being amplified and in what directions. So on the y-axis here, you have the predicted gender ratio, and then on the x-axis, you have the training gender ratio. And if the two were the same, you would get this blue line. But you see these red dots are all over the place. So the ones above the blue line, like pumping, driving, shooting, aiming, tuning, these are all cases where the model predicts more male agents than in the training ratio. Whereas these ones down here, shopping, cooking, microwaving, washing, it's predicting more female agents than male agents. And so there have been methods proposed to try and have these kind of global constraints to get this, the predicted ratio within some margin of the training ratio. And in this particular work, they were using an integer linear programming to do that. And it actually seems to help without reducing the accuracy of the model all that much, which is good. So we won't go into the details here. Okay, so I just wanted to end with a general overview. So we have data set bias, right? So, and this could be a result of sampling bias, but also just what people decide to talk about versus not talk about, and all these other things that we discussed. There are some high-level questions, right? So if we were talking about this kind of task and where it's being deployed in, is it a reasonable goal to want to make this model have equal representation of, like, in our training data set? Should we make our data set have 50% male and 50% female, when the real world distribution of whatever image searching site that we have is skewed towards one or the other. If that bias is useful in making predictions about that, say what Google Images would return, then maybe it's actually reasonable to represent the bias as opposed to artificially fixing it. On the other hand, if we expect that our models are going to be deployed to a much broader population of users and not just stuck on one platform or whatever, then maybe we should make changes to the demographics of the training data in such a way to make it more equally representative. And if you're going to make such changes to your training data, how should you do that, right? What are the guiding principles of how you do that data modification? Like we saw at the beginning of the lecture with the OpenAI method, how did they decide which values to fine-tune their model on, and how did they even write those answers to those questions? Who is validating that? These are all larger questions that are unsolved and challenging. So yeah, any final thoughts?
Is there like a similar word for like race bias? Have the same issue with race?
Yeah, so if you look at there are many papers on racial bias. If you look at the OpenAI paper that's linked in these slides, there's several of the question answer pairs are related to racial issues, like what is the model's perspective of a particular race or religion without any sort of fine-tuning. In some cases, it might be negative, right? It might have learned stereotypes from the training data that you can try and correct. But a larger issue is, can you actually identify and correct all of those in this way? And yeah, how should you do that? Other questions? Yeah.
We were looking at that AI that gives you sort of moral judgments on like little phrases.
Yeah.
I guess, do you think something similar to that instead of like giving judgments on moral situations could give you like, oh, this is a actually accurate answer to a question or inaccurate answer, or just kind of basically it's like this is like a good answer and this is a bad answer. And then could you kind of train something that you sample from your language model maybe several times to get an answer, and then have a system like this that was like, this is the best, like out of all your proposed answers, this is the best one. And then could you then create a data set that now has sort of the model's outputs are the labels, but discard all the ones that were greater algorithms set.
Yeah, so it sounds like you're suggesting maybe we could have a model that takes a bunch of model outputs as input and decides which one of those is the best one to return. This has been looked at in the past. Actually, in many generation models, they don't just run, say, nucleus sampling once, but they might run it 20 times, get 20 samples, and then have some method to pick which one to produce. But that method of choosing is a subject of research, right? So one initial way you might think to do this is like setting aside, factuality or moral judgments or whatever. You might decide to do this via the perplexity of those generated outputs, right? Maybe choosing the lowest perplexity output is going to give you a more accurate representation of what the model actually believes. And of course, like nucleus sampling or beam search or whatever does not give you the exact highest probability output. So maybe you should pick the one that the model thinks is highest probability. However, it turns out that doing that is bad and gives you like these very generic and uninteresting outputs, whereas the ones that the model actually gives lower probability to are the ones that people generally want in many of these applications. So the model is not a good judge of its own outputs, and so that might motivate some sort of external model to do this, possibly with other objectives like factuality or something. Yeah. All right, so yeah, in our final class on Wednesday, we will talk about how you decide how big to make your models and how many iterations to train them for and on how much data. Of course, this is not particularly relevant to any of your final projects, since no one here is training a 100 billion parameter model, but it's still probably interesting to see how the field may change in the future. So see you then.